This is going to be our first lesson in our kinetics unit. Now, what kinetics really is basically what we do is we look at the role of energy in chemical reactions. So there's really only two options. Either energy is being absorbed by a chemical reaction or energy is being released by a chemical reaction. This is going to be mainly a definition word for us. Enthalpy is the stored energy in compounds. Just when you think of that, think of, like, for example, the stored energy in a battery. That's pretty much what enthalpy is. And what we're mainly going to be looking at today is the heat of reaction, otherwise known as delta H. The delta means change and the H refers to heat. So it is the change in energy of a chemical reaction, which is also called the change in enthalpy. Now, we're going to be looking at what we call thermochemical equations. So we know chemical equations. The term thermo just means heat. So what is it really? A thermochemical equation is a chemical equation that has a heat term in it. Heat is energy. The units that we use for energy is going to be the joule or the kilojoule. Those are the main two. And so they are going to be chemical reactions that have joules in it. All right. They are found on table I. I'll get back to table I later. And just a reminder, everything on the left is a reactant. Everything on the right is a product. If it's on the left, we say it's going into the chemical reaction. And if it's on the right, it's coming out of the chemical reaction. So another way of saying that is if kilojoules was on the left, then it would be going into the reaction or being absorbed. We would call that endothermic reaction. And if it were on the right, if you saw the kilojoule term on the right, then it would be leaving the chemical reaction and it would be an exothermic reaction. All right, so think of it like money. If money's going into your wallet, you're gaining it, it's being absorbed. If it's leaving your wallet, you're losing it, it's being released, or exo. Now, here's what the reactions look like. So for an exothermic reaction, this is something that releases energy. Delta H is negative. I'll explain that in a second. And the energy is a product. Okay, so here's what they look like. This second reaction right down here, this is my chemical reaction. This plus water becomes this plus energy. So this is my heat term. It's the term with the kilojoules. And since it is on the right side of the arrow, this arrow right here that we're talking about in the middle, it's on the right, that's how I know it's exothermic. All right, so there's two ways of representing these chemical equations. You could write them with the heat term added into it, or you could write it with the heat term kind of pulled off to the side as a delta H. So if we write it as a delta H, we would say that delta H is negative 65.2 kilojoules. And if we write it into the chemical reaction, we would simply add it to the right. Now notice, this tends to throw people off. Here it's negative, here I'm adding it. And this has to do with which way the energy is going. So if you're losing energy, energy is leaving the reaction, it's going to be on the right. Now, in chemical reactions, we don't like to use negative signs in the actual reaction. Having it off to the side is one thing, like having a negative delta H, that's totally fine. But having a negative in the actual chemical reaction, that's a no-go. We don't do that. And so what we do is we add the energy to the right if it's leaving the reaction, and we add the energy to the left if it's being gained by the reaction. So to compare it, here's an endothermic reaction. This would be absorbing energy or a positive delta H. Energy is a reactant. So here's how it looks. The energy term, so here's my reactant, just like this. And then I'm adding energy to the left side of the arrow. And then here comes all the rest. And so if you notice, in the exothermic, the energy term is added to the right side of the arrow. And in the endothermic, the energy is added to the left side of the arrow. Okay, but we always add the energy to either side. You're never going to see a negative sign in a chemical reaction at this level. So the summary of this is pretty simple. If delta H is negative, the reaction is going to be releasing or losing heat. It would feel hot to us. We would call it exothermic, and we would say that it's added to the right. If it's a positive delta H, the reaction is absorbing heat. It would feel cold to us if we were to touch it, and we call that endothermic, and it would be added to the left. So that's how you tell the difference between an endo and exothermic. Now, the last thing I want to mention is why positive versus negative delta H's. It's actually really easy. If you just took the products, right, and you subtracted, so if you took the energy of the products and you subtract the energy of the reactants, well, if the products are smaller, then when you subtract the reactants, you're going to get a negative number. And that's really where it comes from. That would be like saying, if I had $20 in my wallet before I went to the store, and then I spent some money and now I only have $15 in my wallet when I come back from the store. Well, what's the difference of the money in my wallet? Well, if I took the money that I had when I came back and I subtracted the money I had when I left, my difference would be -5. Well, that's where the negative sign comes from. I can explain that a little bit more in a later video, but let's go to our last topic, which is heats of formation. So a heat of formation is exactly what it sounds like. It is well, this may not be as obvious, but it is the amount of energy gained or released when forming 1 mole of a compound from its elements. So in other words, it's the cost of making 1 mole. And sometimes your heat of formation and your delta H are the same thing, and sometimes they're not. We'll explain. So if we look at this chemical reaction, right, it says it takes 2 moles of C plus 2 moles of H2, and it makes 1 mole of C2H4 as a result. This has to be a balanced equation to do this. So that's the one I wrote it in. We wouldn't normally write the one in. The delta H for this reaction, we can look it up. It's positive 52.4 kilojoules. The delta HF for this is also positive 52.4 kilojoules. And the reason is because in this reaction, what this is saying is it costs 52.4 kilojoules to make 1 mole of C2H4. Well, that is the heat of reaction, and it's also the heat of formation, because the heat of formation, the key here, is the energy needed to make 1 mole of the product. So they happen to be the same thing. Okay, and when we see the next one, it should hopefully be a little bit easier. In this reaction, we take 1 mole of H2, and 1 mole of I2, and we make 2 moles of HI. So the heat of reaction for this is 53.4 kilojoules. We just looked that up on table I. I'll go back to table I in a little bit. But the heat of formation is the energy needed to make 1 HI. So now here is the issue. Think of it like this. It's a simple ratio. 2 HI cost 53 kilojoules, right? So then what does 1 HI cost? This is the type of calculation that you do in your head when you go to the store all the time. If you go to the store and they say, let's say apples are 2 for $3. Well, how much did 1 apple cost? Well, you'd say, well, there's 2 of them. They cost $3. I divide. They cost $1.50 each. Well, you just did this math right here. They're saying that it costs 53 kilojoules to make 2 of them. So what does 1 cost? Well, half that amount. So the heat of formation is actually going to be 26.5 kilojoules. You just take the amount of moles you made and divide your HF by that, or your heat of reaction by that amount. If this were 3, then I'd divide by 3. If I made 4, I'd divide by 4. If I made 50, I'd divide by 50. It's the cost for 1. You can do it in a ratio. You could divide it. There's a number of ways to do it, as long as you understand the concept. Last one, the heat of formation for 1 mole of NO, right? Watch how this works. In this reaction, I'm not making NO. I'm actually taking NO. I'm taking 2 moles of NO and breaking them apart into 1 mole of N2 and 1 mole of O2. That delta H is negative 82.6 kilojoules. This is actually on table I. Now, that's not what I want. I want to know how much would it cost to make 1 mole of NO. So there's 2 problems there. One, I'm breaking it up. I'm doing the reverse of what I need. And then the second problem would be I'm making 2 of them and I want the cost for 1 of them. Let's fix one problem at a time. If I take this entire reaction and flip it, so I just reverse it basically, and I say, okay, well, 1 mole of N2 plus 1 mole of O2 can make 2 NOs. So I just reversed the entire reaction and then I rewrote it. My delta H, notice what would happen. By flipping the reaction, I flip the sign. That's like saying, if I go to the store and I buy something for $20 and then I bring it home and I decide I don't want it anymore. So I bring it back to the store and I return it. How much money do I get back? Well, in a perfect world, you would get $20 back. So if you look at your bank statement, right, let's say you bought it on a credit card, when you bought it, it would say plus $20. And then when you returned it, you would have a negative $20 statement because it would give you a credit. So that's all you're doing, okay? And then the last part, this reaction is still saying it costs 182.6 kilojoules to make 2 NO. So I want to have the amount needed to make 1 NO. So I would just divide by 2. Or you could do it as a ratio. You could do it like this. You could say 2NO cost 182.6 kilojoules. Make sure you include the sign because the sign's going to always stay the same. So therefore 1NO would cost me X kilojoules. You can do it as a ratio and then cross multiply and solve for X, or you can just do it the way I was doing it and divide it out. You get this answer the same way. So that's how you do heat to formation. Last but not least, table I. So here's what table I looks like. The most important part of table I. It's a bunch of chemical reactions, and it gives you your delta H's here, and they have negative and positive signs. Let's say you didn't remember which ones were which. This you really should highlight in your reference table. It says it right here. A minus sign indicates an exothermic reaction. So they actually tell you right at the bottom of the reference table that all the ones I highlighted in orange are the negatives, so they're the exothermics. So now you don't even have to memorize that negative is exothermic. It says it right there. You just need to know where to find it. So these reactions would all have they would all be exothermic. They'd all be giving off heat. They would all feel hot if you touch them. And then all the ones with a positive sign would all be endothermic. They would all feel cold to the touch because they'd be absorbing heat. So just to review, what we did this in this video is we talked about figuring out if something was exo or endothermic, what side to add the energy to, and heat of formation.